Right, so we're recording now, Darren. So what this is a radio program about the second law of thermodynamics. And what it does, it shows the absolute mess that science has got itself into, and is stuck down a dead end, and it's been stuck there since the time of Newton. So this is a big, big problem, and it's all caused by the fact that at the time of Newton, the laws of physics were determined to be absolute causality in the universe for everything. And that turned out not to be the case. What has turned out to be the case is that the laws of mathematics are causality in the universe, because the general theory of relativity has thrown out gravity as a force and replaced it with the geometric or mathematical theory of gravity. But the scientific community has been very, very slow to accept that mathematics is causing things to happen in the universe. So it only has the laws of physics, which has the law of the second law of thermodynamics, which says that systems always seek equilibrium. But what we observe is systems pushing away from equilibrium and becoming more complex and ordered. So there's a huge contradiction. So let's listen to the radio program and we'll clear the contradiction up as we go along.
I hope you enjoy the program. Hello, the second law of thermodynamics can be simply stated thus. Energy spontaneously tends to flow from being concentrated in one place to becoming diffused and spread out. It was first formulated to explain how a steam engine worked. It can explain why a cup of tea goes cold if you don't drink it, and how a pan of water can be heated to boil an egg. But its application has been found to be rather grander than this. The second law is now used to explain the Big Bang, the expansion of the cosmos, and even suggests our inexorable passage through time towards the heat death of the universe. It's been called the most fundamental law in all of science, and C.P. Snow in his Two Cultures wrote, "Not knowing the second law of thermodynamics is like never having read a work of Shakespeare." So what is the second law? What are its implications for time and energy in the universe, and does it appear to be refuted by the existence of life and the theory of evolution? With me to discuss the second law of thermodynamics is John Gribbin, visiting fellow in astronomy at the University of Sussex and author of Deep Simplicity; Peter Atkins, professor of chemistry at Oxford University and author of Galileo's Finger; and Monica Grady, head of meteorites at the Natural History Museum. John Gribbin, before we go into detail of the second law, can you give us an indication of how a law which began concerning steam locomotives came to have such a broad application? Can you give us an overview?
Well, it's because, as you said, it deals with heat. It deals with the flow of heat from one place to another. That's one manifestation of the second law. And, of course, that was hugely important in the 19th century as Britain, in particular, industrialised and the rest of the world followed suit. If you could understand how heat worked, you could build more efficient steam engines, putting it very simply, and so your industry would be more efficient. But it goes hand in hand with developing technology. As you learn to develop better technology and better steam engines, then you learn more about the second law as well. So these things always in science sort of go hand in hand in a ratcheting process. And it goes back even a bit further than that to earlier in the 19th century. There was a guy called Count Rumford who started life as Benjamin Thompson, and he was involved in boring cannon to make cannon for warfare. And he realised that the process of boring out the cannon generated heat in an inexhaustible fashion, which is the important thing. Before then, people had the idea that heat was a kind of a fluid called caloric, which existed in something, and if you heated it by friction, you'd rub it all out and it'd all be used up. And he discovered that no matter how long you kept grinding away at the lumps of iron to make cannon, you kept producing heat. So there's this realisation that heat was a form of energy. It became understood as a form of energy, and energy, of course, is what drives the whole universe and keeps us going, so it's absolutely fundamental.
Can you tell us, just because the listeners will be clamouring to hear this as I am, what's the first law of thermodynamics?
Right, well, the first law is very simple. It's a kind of sort of throat clearing which says that the total amount of energy in the universe always stays the same. And it's been paraphrased as saying you can't get something for nothing. And the second law, in a similar vein, has been paraphrased as saying things wear out. And so you're always losing useful energy. And what matters is that although the total amount of energy in the universe stays the same, you can only do work, as in a steam engine, by moving energy from a hot place to a cold place. And as you do so, some heat gets lost in the process. That's the second law at work. And eventually...
Sorry, Darren, do you want to say something?
Yeah. Do we know then? Because he said there, don't the energy in the universe stays the same.
Yes. So
do we actually know that? Is that?
Yes. So that's an absolute that you can test with physical experiment.
Right. Okay. And also, I'll wait till a bit later on about the complexity stuff. But good. Yeah.
But so you can already hear that they're starting to say things which don't seem to make sense. Because if you look at the formation of a snowflake, energy is actually being removed from the system as it cools down, and suddenly it becomes more complex. So that doesn't agree with the experiments that you do in physics. But as long as you ignore those and don't show them to university students, nobody notices. So let's get back to the program.
Yeah. As this goes on and on and on, the whole universe will end up at the same temperature. And if everything's the same temperature, you can't do anything useful. You can't run a steam engine in which both bits of the steam engine are at the same temperature. And so this is the idea that things will eventually wear out entirely. And that ties in with what you were talking about, the arrow of time. There's a past when things are lively and interesting and heat flows from one place to another, and a future where everything's cold and dark and worn out.
Throughout this...
So there's a contradiction that the past is interesting. Well, that doesn't really mean much, but the universe now is far more interesting than the clouds of hydrogen at the beginning. There were no elements, no stars, no solar systems, no biological life. So that's really showing up the contradictions that come out from only having the laws of physics as an explanation for causality.
First part of the program, we're going to use the steam engine as a metaphor for big bangs, for all sorts of change, which we'll come on to. Peter Atkins, can you introduce us, can we go further into the steam engine and tell us how the theory grew out of the practice? Because that's one of the fascinating things. Is these men are working away, making this thing to go along railway lines, and the theory develops alongside or around it. Can you tell us how, say, the French physicist Sadi Carnot, what he did about it?
Yeah, I think there are really four people who constructed the second law. One is Sadi Carnot, another was William Thomson, Lord Kelvin later, and then there was Rudolf Clausius, and finally there was Ludwig Boltzmann, and each made a very special contribution to understanding. Carnot looked at a steam engine and tried to identify what was the limits of its efficiency. Everyone thought at the time that England was producing its munitions, it was pumping its wells and so on, pumping its mines with steam, and the French were terrified, so there was a huge interest in France on making their machines more efficient. And Carnot looked at the structure of a steam engine and tried to think what it was that determined its ultimate efficiency. Most people at the time thought that it might be changing the pressure, might be changing the working substance from, say, steam to air and so on. But Carnot came up with what turned out to be an absurd idea in the views of his contemporaries, that it was only the temperature. That, as John just mentioned, a steam engine really consists of three bits. There's the hot reservoir, there's the cold sink where you throw away some heat, and there's the gubbins in between, really, the piston which converts heat into work. And Carnot, by thinking about the machine, decided that it was only the temperature of the hot source and the temperature of the cold sink that determined.
So we've talked about this before, Darren, where we've said it's the difference between things that makes them work together.
Yes.
So what's making the steam engine work is the difference in temperature between the hot boiler and the cold outside temperature of the train.
Right, okay.
But of course, the one thing that you notice very quickly about the train is that it doesn't self-assemble. Whereas things like solar systems self-assemble from something which is just dust and rubble into a very accurate clock. A snowflake self-assembles into a beautiful symmetrical pattern, and human beings self-assembled from the periodic table. Now that doesn't sound like something going from order to more disorder, but as long as you keep avoiding those questions, you can just keep going.
Right. Okay.
Ultimate efficiency.
What were the briefly the chief modifications that the other, or extensions that the other three that you mentioned gave to it?
Well, Carnot's views were seen to be so absurd that they were ignored, which I suppose for England was a good thing. Then his book sort of survived in print, and Kelvin came across it and started to think about it in more detail. And he came up with the view that really the most important part of a steam engine was not the hot bit, it was not the piston, it was the cold bit. And he said effectively, and this is yet another statement of the second law of thermodynamics, that steam engines don't work unless you've got the cold sink. The next person to come along was Rudolf Clausius, and he said something that we all know anyway, that heat doesn't flow from a cold object to a hot object.
And finally, can briefly, you've got the other one to go.
And Boltzmann.
Yet another man whose ideas were dismissed as completely absurd.
Boltzmann, I suppose, was short-sighted physically, but he saw more into the nature of the world than anyone else, and he identified the molecular basis of the second law, why it is that what we have been saying is true in terms of the behaviour of individual atoms and molecules, and that's, which we'll come on to, I think is a major revelation about why the world works in the way that it does.
Monica Grady, Kelvin and Lord Kelvin understood that you were to let some heat escape if other heat was to use to power the turbines. In other words, some heat had to be jettisoned. Now, where does this fit in? I mean, we've got two very powerful introductions from John and from Peter. Where do we go next, then, to sort of build up the theory alongside the steam engine?
Well, we have to look at where the heat's going to and what this system is. John referred to equilibrium, and you tend to get equilibrium in a closed system, and of course in a closed system you won't get this work happening.
Can you just tell the listeners what you mean by a closed system?
Oh, a system where nothing can escape. Like
a sealed box?
Like a sealed box. A sealed box is a closed system. You're not putting heat in, you're not allowing any heat to...
So it's very important at this point to say that the solar system is a closed system. There's no flow of heat going in, no flow of heat going out, except the tiny amounts coming from the stars. So it's not like the Earth, which has sunshine pouring into it every day. And yet the solar system self-assembles from nothing but dust and rubble into a very accurate clock. That needs an explanation.
Right.
That explanation cannot come from only the laws of physics. The laws of physics are all correct, but they're not enough to explain the self-assembly of a very accurate clock. So that's the problem.
To escape, you have a closed system. Now, in a system like that, you're not going to be able to do any work because you're not going to get a change, you're not going to allow heat to escape. And so the big thing about the steam engine, as Peter Atkins referred to, is this cold sink. And there isn't a big sort of heat absorber in a steam engine. The cold sink is the outer universe, and the Victorians tended to look at things, because they didn't understand the universe, had got no concept of how enormous the universe was. They looked at things on a much smaller scale. But now we realise that actually when we're looking just at a simple steam engine on a railway in Britain, it's putting heat out into the atmosphere, which is, travelling throughout our around the globe, which then has implications within the solar system, within the galaxy, and so on. So the whole system is the universe, and that is where the heat is gradually dissipating to. So we must look bigger than just a simple cold system.
The word that comes in, there's one word that is disorder. Things go from order to disorder. From the closed system of order, one can say, to outside, the heat is more disordered than the liquid. The liquid is more disordered than the solid. So order to disorder is the progression. And then the word entropy comes in.
Right.
So would you just explain why it came in and what it means, what its usefulness is in this discussion?
Well, entropy is a measure of the amount of disorder in a system, and if you think of a solid crystal, that's a very, very ordered system. You have atoms, you have ions perhaps vibrating in a lattice, but it's quite rigid. If you then melt or dissolve that solid, you have liquid where you have molecules, atoms are able to move around much more swiftly in a much more disordered way. And then think of converting that into a gas, which would fill a whole room. Think of an ice cube going to a puddle of water, going to steam. You have something that would then fill the whole room. You can't then predict where that molecule is, which molecule is going to hit a wall. The whole thing becomes more disordered as you heat it up, and you can't go back again in a predictable fashion. You can't say, I'm going to take that molecule and put it there. And this is where John referred to time's arrow. This is where time's arrow comes in, as we have this increase in disorder, this increase in entropy in the universe. It seems to be always pointing in one direction. We can't reverse entropy. We can't decrease entropy.
So that is just absolute nonsense. We can't decrease entropy. So the universe starts out as clouds of hydrogen, which are amorphous. That means they have no particular shape, like the Eagle Nebula. And the clouds of hydrogen evolve into stars and elements, which evolve into more elements, which is clearly more ordered than a cloud of hydrogen. The star explodes, and then because you've now got the elements, can evolve into a solar system, which goes from dust and rubble into a very accurate clock, and each gas giant is a clock within the big clock. And it's the difference between the size of the sun and the planets which allows that to happen. It's the difference between the size of the gas giants and their moons which allows it to happen. But you can't explain the formation of the clock using the laws of physics. They're too simple. So once this is pointed out to people and they can see it, it's clearly huge contradictions. That when we look around us, all we see in the universe, nature is defined by mathematical patterns everywhere, from galaxies to snail shells to rivers. The whole lot of it is defined by mathematical patterns which have come from disorder. So something's wrong. Something's really wrong. What's wrong is that you can't explain the formation of the mathematical patterns from the simple laws of physics. You can explain the mathematical patterns if you say that mathematics is causal in the universe. So it solves the problem.
On this universal scale.
So in that explanation, we're always losing energy, and we're always moving towards disorder, and we're always moving towards more heat.
We're not losing energy, we're just sort of changing the form of energy, if you like, or
We're
spreading...
losing useful energy, I should say. We're losing useful energy, yeah.
We're spreading it all out. We're making it more even. We're going from, say, to use a water analogy, we're going from a waterfall where you've got water going from a high point to a low point. We're going more to an ocean where everything is spread out at the same level.
So just to summarise, from this industrial object came these theories which now underlie notions as to how the whole thing operates. Peter Atkins, talking, what's happening to the universe at large then when these heat? How do we transfer the steam engine, as it were, to the universe at large? With this theory.
Well, I mean, the briefest statement of the second law, which I think we ought to focus on, is that things get worse. If you like, energy has both quantity and quality, and entropy is a measure of the quality of energy.
So, sorry, Dan, go on.
What does he mean there by things get worse? Like,
Well, this is the problem, that when you don't know what the answer is, you end up talking nonsense. I mean, complete nonsense. So
yeah,
human beings, the human brain, self-assembled from nothing more than clouds of hydrogen. How is that getting worse?
exactly.
Exactly. Now, the science community avoids these problems or gives an example like only in a closed system. But if the solar system is a closed system, your example doesn't work.
Mm.
And if we now put the correct answer in that things have been driven mathematically, and therefore I've got the laws of physics, which is the first set of mathematical rules, and then layers and layers and layers and layers of more mathematical rules on top, now I've got access to mechanisms which I don't have if I just look at the first set of physical laws, which is the laws of physics. And now we've discovered the laws of chaos, which is another set of physical laws which nobody was suspecting was there. We can now describe systems which push away from equilibrium.
Right, okay.
So that's never been available to us before the use of computers.
Yeah, when you say push away from, oh, sorry, Peter.
Yeah, when you say push away from equilibrium, what that means, system, if I put a cup of tea on the table, the tea is in a state of non-equilibrium with the temperature in the room. So the tea cools down, the room heats up until they meet a point of equilibrium. They're both the same. Then nothing else happens.
Right.
So that's simple physics.
Yeah.
But if I cool some water down in the atmosphere, it turns into a snowflake. Well,
yes.
A snowflake is not an equilibrium because it's very symmetrical. So it's not just molecules bouncing around a room. It's a very, very non-equilibrium state. So, and before you find the laws of chaos, you can't understand systems pushing away from equilibrium. It doesn't make any sense. But as Robert C. Hilborn points out in his book, Chaos and Nonlinear Dynamics, that the study of chaos in physical systems, chemical systems, and biological systems is the study of systems which are pushing away from equilibrium. And what he says clearly, and this is a quote, physics is not appropriate here. So you're studying the behavior of physical matter, but physics is not appropriate here.
Right.
So that book should have woken up the world, but it didn't.
Right.
Increases, that is, as the world becomes more disorganized, so the quality of energy degrades. But the crucial point is that although energy may disperse, you can tap into that dispersal and use it constructively. So if you think of the engine in a car, the fuel is burning, and the energy that is released in that way spreads, and also the carbon dioxide and water that is produced when the fuel burns also disperses. But your engine is a way of tapping into that dispersal, and you use it to drive pistons.
So the question we have to ask there is, how does the dispersal of no energy in the solar system cause it to self-assemble into a clock? There isn't an energy source which is causing the order of the solar system to increase. So it's absolute nonsense.
Okay.
If you say that there are mathematical rules which are driving the self-organization of the solar system, and we now know what those mathematical rules are, and that is the conservation of information and feedback loops, i.e. periodic repeating orbits, which conserve information. And if you've got a big difference between the size of the sun and the planets, you reduce the differences between the orbits until they all harmonize.
Right.
So the moons of Jupiter have a 4-to-1 ratio. It's all harmonized. And it's not harmonizing due to a dispersal of energy. It's harmonizing due to mathematical rules which
Right.
cause music to harmonize. It's exactly the same thing. So let's get back to listening to some more.
And so on. And then you can connect those pistons through gears to bricks, which you build into a cathedral, and so on. So you can use this dispersal constructively, and that's the crucial idea. And you can transform the same idea to, for example, when you eat in the morning, the food that you ingest undergoes metabolism and so on. It breaks down, it releases energy. Think of it as fuel once again. And instead of having a mechanical train of pistons and gears like in a car, what you've got is a biochemical train of gears and so on, which can be used to, not in this case to put one brick upon another to build a cathedral, but to put one amino acid next to another.
So you can hear this analogy is utter nonsense when you compare it to the solar system. So where's the fuel that's powering the solar system and causing this order to increase? There isn't any. So we really are deep in nonsense by this point. Embarrassingly so.
To build a protein. And you can be, so in other words, as you eat and disperse energy, so you grow. And the processes of life continue. And you can be even more fanciful, if you like, that if you think of the random electrical currents in your brain becoming organized by the same kind of process in order to, you eat, and through the biochemical processes that occur and drive the neurophysical processes in your brain, you think. And so an act of creation, like writing a piece of poetry, giving this talk, an act of gallantry and so on, are all ultimately driven by the dispersal of energy. And that is why it is so far-reaching.
Both those examples, of course, that ultimately depend on energy from the sun. The fuel we use in the car has come from stored-up sunlight in plant remains, and the food is ultimately from stored-up sunlight in plants. And what's happening is that we've got a negative entropy happening locally because the sun is making positive entropy on a much larger scale.
I want Monica to unravel that a bit. A negative entropy happening locally. Can you just describe how the sun works in our system and prevents our own planet from being a closed system, and therefore, just stay with our planet and the sun at the moment, and therefore has the effects it has on the entropy here? Could you just take that on a bit?
Yeah, certainly. I mean, if you look at life and this building up of life, you might think, well, that is something that's becoming more complex. But when we look at a larger system, like the system which incorporates the sun, then we see what's actually happening is the sun is this enormous ball of hydrogen, and the hydrogen is fusing together to become atoms of helium. And as it does that, it gives out heat and light. And that heat and light bathes the earth. It powers our atmosphere, our climate, our weather. It powers the carbon cycle, the water cycle. So it powers the whole of life on Earth.
So let's move a bit further out now, John Griffin, and go to the Big Bang, where presumably if disorder is coming from order, then we can look for a point where there was only order, and we inevitably go back to the Big Bang. Is that right?
No, that's wrong. It's a big puzzle, and it was a big puzzle until quite recently. The Big Bang, the birth of the universe, seems to have been a very disordered state, and we now know this from looking at the famous background radiation, the microwave background radiation, which gives us a picture of what the universe was like when it was only a few 100,000 years old, a few 100,000 years after the Big Bang, at about 13 billion years ago. The universe was very smooth and well distributed, and it was a fairly uniform.
So he nearly said well organised and just stopped himself in time.
Right, okay.
So what he's got is uniformity.
Yeah.
The universe was bathed in uniformity, and that uniformity collapsed into ever-increasing complexity. And we are part of that, because what we do is increase the complexity of the matter around us.
Yeah.
So the universe is being driven up a complexity gradient by mathematical rules, and the science community can't see that. Because it's only got physics rules. The laws of physics are far too simple and only seek equilibrium.
Yeah, even at the beginning, like I noticed, like just to go back to the steam engine example, I think it was the lady scientist. She said that something about steam engines improving. Well,
Yeah, increasing efficiency.
But don't that mean even steam engines have gotten more complex?
Well, they've got more complex, but that's not really the argument, because the argument is if you've got an inflow of energy like sunshine onto the Earth, you can increase the efficiency of driving complexity
right
at the biochemical level, which is hideously complex compared to a solar system. I mean, really. Now, all you've done is increase the efficiency. What you haven't done, you've said there's a flow of energy. Well, that's the battery.
Right.
But all you've got is the battery. What about the clock? That's the bit which is self-assembled. And that's the dynamics of the self-assembly of a cell is millions of times more complex than the self-assembly of the clock.
Right, okay.
So you've got this inflow of energy, brilliant, but that doesn't explain the mechanism by which the cell self-assembles. That's been left out of the argument at the minute.
Right, okay.
So until the end of the program, it's still left out of the argument.
Ah, okay.
Of hot gas. Now, what's happened to the heat is that heat has degraded and it's cooled down to become the very cool background radiation. But what's happened to the matter is that it's been turned into stars and galaxies by gravity, and you have actually made a much more structured system out of a disordered system thanks to gravity. And gravity has a...
So there is just deep in contradiction. You've made a much more structured system thanks to gravity. Well, gravity is a law of physics, true or false, and you've gone from disorder into order. So it's contradiction all the way.
Right, okay.
Remarkable property, which wasn't properly appreciated until relatively recently, is that it runs this whole process backwards. It can make entropy run backwards and create order where there wasn't order before.
So that is a terrible, terrible thing for a scientist to say. It can create order where there wasn't order before. And gravity, or physics, is causing time to run backwards. Oh, come on, give us a break. it really is that bad.
Can you develop the idea, Monica Grady, of the heat death, the universe following an inevitable course towards what will be a heat death of the universe because of the working of the second law of thermodynamics?
Yes, this follows on from what Peter was saying about this constant expansion and the constant flow of energy. As coming back to our star, it converts hydrogen to helium, gives out heat. The hydrogen will eventually run out. The helium will be converted to carbon, giving out more heat. This is happening in all sorts of stars. Some stars explode, become supernovae, again giving out huge, tremendous amounts of energy. And all those processes within our galaxy, and within every galaxy, are leading towards a gradual equalization of the energy within that particular system, and then spreading out between the different galaxies. And each galaxy is not in isolation. It's surrounded by a halo of material that we can't see. It's sort of within a sea of dark matter. So within our whole universe, gradually the stars will build up elements, explode as supernovae, turn those elements back in to the interstellar medium, start new stars forming. It's a constant cycle, but eventually that cycle will run out of hydrogen. All the hydrogen will have been converted into other elements. It was the hydrogen that was formed in the Big Bang, and gradually the whole thing will become dissipated throughout the whole of the universe, and the temperature will gradually have dropped and equalized all over, and we'll go, this is the heat death. By that time, everything is the same temperature all the way through, and no work can be done.
So what she just said there is true. But we already know that there's a mechanism in the universe in which you can change pure matter back into radiation at a high temperature. And we use that in hospitals every day in PET scanners, positron emission topography.
Right.
Now, matter and antimatter, when they meet, turn back into pure radiation, which is much higher temperature. So there is a mechanism in the universe in which you can reverse the cold matter and turn it back into pure radiation, but nobody's thinking about it.
Right.
So as long as you don't talk about things, because we think in language, people don't even think about it. But this program just really gets worse and worse.
In Peter Atkins, in your book Galileo's Finger, you use an example of an astronomical clock in Prague to illustrate the illusions, you put it, of complexity and the reality of growing disorder. It's a very good, it's a very clean metaphor. It takes us on from the steam engine. We go from a steam engine to a clock as we wend our way. But can you just say why you think that illustration is important? And I'll come back to you in a second.
Because you've got a process which is driving a complicated collection of interacting gears, if you like, which give rise, I think, as I say there, to the Acts of the Apostles, as these images move around the clock in Prague. It really summarises what we've all been saying, that you've got essentially a driving force, which is simply the natural tendency of energy and matter to disperse. In this case, it's the falling of a weight, which disperses its energy through friction and so on. So it's irreversible in the sense that the weight falls, the energy is distributed into the rest of the universe. But there are gears that are driven by this fall, and the gears drive, one apostle out through one door, another apostle out through another door, and they do funny little things and so on. And that really captures what we are. That really captures the basis of the biosphere. In our case, as Monica said, the driving force is the sun. That is the hot source of this solar steam engine. That it gives rise to. It dissipates its energy, but the vegetation on Earth, if you like, provides an analogue of the pistons and the gear wheels of a real steam engine.
Now that isn't true, because the gear wheels of a real steam engine don't self-assemble. So
Right,
it's
okay.
absolute nonsense. It's absolute nonsense.
And drives the processes of growth on Earth. And then we use the vegetation that the sun has driven to drive ourselves. So it's a whole sequence of one object using a particular fuel to create more fuel for another object.
The business of order to disorder, things becoming more disordered, seems to be contradicted by evolution. One of the things that happens in evolution, lots of different things happen, but one of the things that happen is that life becomes more complex, and I suppose our brains are the best example of that, becoming more and more complex. So how is this second law of thermodynamics of things getting worse, things becoming wearing out, things more disordered, and we're becoming... Can Monica answer that? Monica, have a go at that first.
You're still looking at a very small system there, where you're looking at...
It's still part of it. I mean,
yes, we're part of the system. So if we're looking at something becoming more complex in this particular part of the system over here, that doesn't necessarily mean that it's not echoed by an increase in disorder somewhere else.
But how does
so
that...
again, it's still all being powered by the sun, this increase in complexity.
But how does that...
So that is absolute nonsense, because the increase in complexity in the solar system doesn't come from an external energy source. The solar system itself increased in complexity.
Right.
All by itself. It's a closed system. It doesn't have an external driving source of energy. It's a closed system. So we're deep in nonsense now.
But sit with the idea of things becoming more disordered therefore less organised, when a lot of that's happening in evolution is becoming more complex and more organised. Now, your explanation is, but disorder is happening in somewhere else, and by this magic inevitability of equilibrium, the disorder somewhere over there, way over there, with a wave of the hand, is balancing up the increasing complexity and order here. But where is over there, connected. And why is complexity happening here?
They're connected. The interesting things happen, what you're calling complexity, interesting things happen where there's a flow of energy. And so you have to be sitting in the flow of energy in order for interesting things to happen, whether it's a waterfall or a human being. Energy is part.
So you see there, it's complete nonsense, because there's no flow of energy self-assembling the solar system into a clock.
Right.
It's not the heat from the sun. There's nothing to do with it. So you can see, but this is where the science really does unravel, and Melvin Bragg is quite happy to say so.
Passing through the system.
Yeah.
So that energy has to come from somewhere, and it has to be connected to you. And in our case, it's coming from the sun. So the increase in entropy produced in the sun is creating the energy flow, which makes us produce a corresponding but smaller change in the opposite direction.
But doesn't it give you any pause that this is contradicting the second law of thermodynamics? That things are not getting worse, that things are not wearing out, that things are not becoming more disordered, things are getting more complicated and more efficient and more ordered.
We are local abatements of chaos. We
are local abatements of chaos. Is that really it? Is that all you can say? We're local abatements of chaos. The human brain.
What does it even mean?
It doesn't mean anything. Anything at all. Local abatement of chaos means that in a local situation, human beings are not chaotic. We produce beautiful artwork, a ballet, works of Shakespeare, and that's all a local abatement of chaos. Is that really the best you can do? A local abatement of chaos, really.
We are driven into complexity by the creation of greater disorder elsewhere.
But where is this elsewhere you keep saying is going to solve it?
It's on the sun, ultimately. Right. I mean, it's the dissipation of energy on the sun, which is driving events in the vegetation on Earth. Animals eat the vegetation. They use that as fuel. That drives their processes, including their growth, their reproduction, and their thinking. And our thinking.
I can give you.
It's like, in a sense, the analogy to keep in mind is if you sat in front of a screen in which there was a weight on the floor, and you saw the weight go up, you'd think it was a miracle. But then if you look behind the screen and you see that, in fact, there's a weight behind the screen which is actually falling down and pulling the front weight upwards. So it's when you look at the whole thing that you realise that there is a simple explanation. That is, energy is dispersing and driving the events which you think are giving rise to complexity. They are in fact...
So when you look, imagine standing in a rainforest. And that, billions of years ago, was nothing more than rocks and water. Same elements. And then you insult somebody by saying, this rainforest is what you think is complexity. There's more complexity in a single cell in the rainforest than a car. So what an insult. This is what you think is becoming more complex.
Yeah.
What an insult. It's absolutely shocking.
In fact, giving rise to disorder and locally to complexity.
I mean,
it's a neat explanation. I mean, it's very good. You're probably absolutely right. It just seems something getting away with it going on. Monica.
Well, you would say that as a local abatement of complexity, wouldn't you?
You would say that as a local abatement of complexity. So that is the description of a human being and all the fabulous things that we're capable of in nothing more than a local abatement of complexity. Really. Is that the best you can do? Science world? Come on, I'm going to take you on. Absolutely.
Yeah.
Well, I've never been paid such a fulsome compliment in my life.
If you just consider the solar system, I mean, we are just one planet within the solar system, and the complexity seems to be increasing on our planet, but not on other planets as far as
What? A load of nonsense. The complexity seems to be increasing on our planet. The solar system itself is a vast increase in complexity from the clouds of hydrogen from which it evolved. That's the true or
Yeah.
false question. It's absolute nonsense.
So she says it seems to be getting more complex. It's not. It is getting more complex.
Yeah, if you can trust your own eyes and your own brain,
Yeah.
and you trust that what you see is reality.
Yeah.
You can touch and what you can feel and what you can see and hear, that's reality. Unless we're all living in a dream.
Exactly. We only have to look 100 years back to see how much more complex is society. You know what I mean? The invention of the internet and stuff like that. Is that what they mean?
Yeah, it is. But as long as you leave all the important examples out, and the solar system is the best example. So she says that complexity is only increasing on planet Earth. But the solar system is a clock, a very accurate clock. Now that's self-assembled from dust.
Right.
So come on, give us a break.
Yeah.
Isn't a clock more complex than dust?
Mm.
So you can see how bad it gets.
As we're aware, there isn't this increasing complexity, the increasing evolution of a series of life forms on other planets, as far as we know, as far as we can see. So we are just a very, very small neighbourhood.
I can give a much more homely example of this. An ordinary domestic refrigerator. If you've got a domestic refrigerator, it's by a miracle. It's making things colder inside. It's taking heat from a colder place to a hotter place, and it's throwing the heat out the back and getting warm. So it's not violating thermodynamics if you look at the bigger picture. And if you have a sealed room and you open the door of the fridge inside and leave it running, what happens to the room? It doesn't get colder because the cold's coming out of the fridge. It gets hotter because the waste heat from the refrigerator is warming the room, and because no process is 100% efficient, so you're generating more heat outside than you are making cold inside. And that's what we're like. We're like the inside of a refrigerator bathed in the outside that surrounds us in the solar system.
I think we'll stop there, gentlemen and ladies. Thank you very much. Thanks.
I mean, that would be a good place to stop, because look at the solar system. Is that driven by heat? Is the increase in order driven by any heat source? Is the heat from the sun driving all the solar system into being a clock? Absolutely not.
Right.
Any human being can work that out for themselves. They don't need a physics professor to say that.
No.
Heat, the dispersion of heat, does not drive the self-organization of the solar system or a galaxy.
Mm.
Especially, we need heat to provide energy so that we can increase the efficiency of the self-assembly of molecules in biology. But the self-assembly is not driven by the heat. The heat's just the battery.
Right, okay.
The complexity is that all the bits are in the right place. Every piece of DNA has billions of atoms all in the right place. Now, you've got the energy to put them in the right place, but what's putting them in the right place? That's the question. How does each atom know where to go?
Mm.
So it's like me having the energy to put the bricks of a cathedral in the right place. So I've got the energy, but I've got to know where to put them. Where's that coming from in the solar system?
Yeah.
So it's not just shocking, it's absolutely hideous.